of this presentation. Our first key finding relates to the cement job. BP relied on the expertise of Halliburton, the cementing services provider, to recommend a cement slurry appropriate for this well. The BP team was responsible for assuring Halliburton's work and accepting its proposal. It was clear from the event that the cement did not isolate the hydrocarbons. The challenge facing the investigation team was to determine what happened without access to actual samples of the cement slurry used in the Macondo well. Therefore, we had an independent laboratory analyze the slurry design and also create and test samples based on that design. Through our investigation of the cement job, we noted the following critical items. First, the high percentage of nitrogen in the foam cement made it difficult to create a stable foam slurry. Second, there were no fluid loss additives used in the entire cement slurry. Third, a relatively small amount of cement was pumped in relation to the displacement volume, increasing the likelihood of cement contamination. And fourth, Halliburton did not conduct comprehensive lab tests that could have identified potential problems with the cement. The independent laboratory constructed representative cement samples based on the slurry design and demonstrated that cement stability could not be achieved. Therefore, we've concluded that the foam slurry likely experienced nitrogen breakout, resulting in nitrogen migration, slurry contamination, and incorrect cement density. Our investigation of the cement job also included an analysis of BP's decision to use 6 centralizers and a long string production casing in the well. We concluded that the long string design itself was sound and consistent with other wells in the area. BP had 15 additional centralizers on the rig, but they were incorrectly thought to be the wrong type. Although the 6 centralizers were placed across the main hydrocarbon production zones, the decision to use 6 rather than 21 centralizers increased the possibility of channeling above the main hydrocarbon zone. This matters only if the flow came up the annulus and through the seal assembly. We believe that BP and Halliburton working together should have better identified and addressed the issues underlying the cement job. Improved technical assurance, risk management, and management of change by BP personnel could have raised awareness and led to better decisions regarding acceptance and implementation of the cement proposal. Similarly, with improved engineering rigor and testing, Halliburton could have better identified the reliability of the foam cement slurry and communicated the risks to the BP well team. The investigation team's next task was to determine the actual point of entry for hydrocarbons into the well. We examined and analyzed every plausible entry point. As a result, our second key finding is that the initial hydrocarbon entry occurred at the shoe track and that its mechanical barriers therefore did not isolate the hydrocarbons. Our conclusion is based in part on hydrostatic pressure calculations, well flow modeling, and an analysis of data recorded during the successful static kill of the Macondo well. The shoe track has 2 types of mechanical barriers, the cement in the shoe track and the double check valves in the float collar. The investigation team believes that the shoe track cement failed to act as a barrier. The team has not established whether this failure was attributable to the design of the cement, contamination of the cement by mud in the wellbore, commingling of the cement with nitrogen due to nitrogen breakout from the foam cement, swapping of the shoe track cement with the mud in the bottom of the well, or some combination of these factors. Hydrocarbons were able to bypass the float collar check valves because they were damaged, they never properly converted, or they simply failed to seal. The evidence shows that the flow came up through the shoe track at the bottom of the production casing. Therefore, the decision to use 6 centralizers likely did not contribute to the outcome. The third key finding is that the negative pressure test was accepted, even though well integrity had not been established. The negative test was conducted to confirm the integrity of the annulus cement, shoe track, casing, and wellhead seal assembly. Looking back, the investigation team believes there were several issues associated with this negative test. First, at the start of the test, the annular preventer allowed approximately 50 barrels of spacer to pass into the BOP. This may have inhibited the pressure readings on the kill line. Second, the bleed-off volumes we examined were in excess of what should have been expected, indicating communication with the reservoir through failed barriers. And third, rig personnel found that drill pipe pressure had increased to 1,400 psi with no flow on the kill line. The investigation team believes this reading should have resulted in further inquiry into the well's integrity. Instead, the abnormal pressure was attributed to a phenomenon called the bladder effect. Ultimately, the negative test was incorrectly deemed a success by BP and Transocean rig personnel. A more detailed procedure would have helped BP and Transocean personnel to implement and interpret the negative test. The investigation's fourth key finding is that the influx of hydrocarbons into the well was not recognized until it had entered the riser. Well control principles rely on early influx detection and effective response. The investigation team examined real-time data from the rig, conducted dynamic flow modeling, and reviewed witness accounts in order to reconstruct the key indications of flow that we believe were not observed or recognized. It appears that there were a number of indicators of hydrocarbon influx that went unobserved or unrecognized. First, from 2058 to 2108, the drill pipe pressure should have decreased. Instead, drill pipe pressure increased by 100 psi at a constant pump rate starting at 2101. By 2108, a 39-barrel gain had been taken. Second, from 2108 to 2114, the drill pipe pressure increased by 246 psi with the pumps off. Pressure should not have changed during this period. And third, by 2131, an estimated 300-barrel gain had been taken. Over the next 5 minutes, the drill pipe pressure increased by 556 psi, again with the pumps off. These indicators should have been observable, but it appears the first well control actions were not taken until about 2141, by which time an estimated 1,000-barrel gain had been taken. The investigation team has not reached a conclusion as to why these indicators were not observed or recognized. We note, however, that simultaneous operations were occurring on board the vessel at this time, including mud pit cleaning and mud pit transfers, which may have masked the indications of a hydrocarbon influx. The fifth key finding is that well control response actions did not regain control of the well. Upon recognizing an influx, the well must be shut in, and if necessary, hydrocarbons diverted safely away from the vessel. The investigation team believes that the response on April 20th was not typical of a rig crew that was aware that a significant well control event was occurring. For example, in retrospect, there was about a 40-minute gap between the first indication of hydrocarbon influx and the first well control response. Roughly 8 minutes later, the first explosion occurred. When action was taken, the diverter was closed and the flow was routed to the mud gas separator. Also, at that point in time, it appears that an annular preventer was activated, but apparently did not immediately seal. The BOP sealed about 6 minutes later. The investigation team believes that the time for effective emergency response was significantly shortened because initial indications that hydrocarbon had entered the well went unobserved or unrecognized. The sixth key finding is that the diversion of hydrocarbons to the mud gas separator resulted in gas venting onto the rig. In a well control event, the riser diverter can be closed and the fluids directed to either the overboard diverter lines or the mud gas separator. Based on testimony and interviews and an analysis of photographs and well flow data, we believe the flow was diverted to the mud gas separator. The mud gas separator is designed to remove small amounts of entrained gas, but not the significant volumes experienced here. large volumes would generally be expected to be sent overboard via the 14-inch diverter line. As gas dispersed across the vessel, potential ignition sources were enveloped in a flammable vapor cloud. The seventh key finding is that the fire and gas system on the Deepwater Horizon did not prevent hydrocarbon ignition. Gas dispersion modeling conducted by the investigation team shows that rapid spread of gas across the vessel covered the main deck and moon pool areas, overwhelming the secondary protective devices. The investigation team believes that the gas likely entered the engine rooms through the main deck air intakes, resulting in engines going into overspeed. These engines were one potential source of ignition. The eighth and final key finding is that the blowout preventer did not seal the well. The investigation focused on the BOP's emergency systems and why they failed to seal the well after the initial explosion. The investigation team identified issues that we believe interfered with the operation of the BOP. First, the initial explosions and fire damaged the control cables, called MUX cables, and the hydraulic lines. The MUX cables are critical to BOP operation because they provide electronic communication and electrical power to the BOP control pods. This is likely why the emergency disconnect system failed to activate the blind shear ram when it was triggered by personnel on the bridge of the Deepwater Horizon. Second, we believe, based on testing done at the direction of Transocean, after both control pods had been retrieved, that the automatic mode function, or AMF sequence, did not complete. The AMF should have activated automatically, without crew intervention, when the MUX cables and hydraulic line were damaged. At least one operational control pod was required to activate the AMF. However, based on testing, there was a defective solenoid valve in one control pod and insufficient charge on the batteries in the other control pod. We believe that the ROV intervention to simulate auto shear conditions likely activated the blind shear rams, but they failed to seal the well and hydrocarbons continued to flow. The investigation team has not determined the reasons for the failure of the blind shear rams to seal. Presence of non-shearable pipe across the blind shear ram, insufficient hydraulic power subsea, and prevailing flow conditions are among the potential causes of failure. The investigation team also found indications of potential weaknesses in the testing regime and maintenance management system for the BOP. The BOP is a complex device, and more may be known when it is fully examined. In summary, as I noted at the outset, the investigation team concluded that there was no single action or inaction that caused the Deepwater Horizon accident. 8 safety barriers were breached. The accident was the culmination of a complex and interlinked series of mechanical failures, human judgments, engineering design, operational implementation, and team communication. These involved a number of companies, including BP. This presentation of the report's findings is intended as a high-level overview. The full report is available on BP's website. BP's senior management has accepted all of the team's recommendations, which address changes that should be made in drilling and well operations, as well as contractor and service provider oversight. Finally, in the course of conducting the investigation, the team learned of many brave acts by people on the night of the accident. I would like to close by recognizing those individuals for the lives they undoubtedly saved and by extending our sympathies to the families of the 11 men who died that night and to the communities subsequently affected by the spill.